Today we're going to talk about how quaternions can be used for rotation. So for that matter, we are going to start with two results. The first result is the rotation formula. So I will require this result that allows us to rotate a vector. So we have, if we have an axis of rotation given by a vector n, and we want to rotate a vector v through a left-hand rotation of an angle theta, we have seen before that the formula that allows us to do that is a v is the rotated vector. It's given by u cross, let's say this is u, and then the rotated vector will be v. So our v is given by u dot n 1 minus cosine of theta plus u cosine of theta plus u cross n sine of theta. So that's the result number one that I will require. If it's so required. And we also will require the definition of a quaternion product. So the quaternion product is given by this formula. So I will also use this result. And today will be all about how those two connect. How can I use this algebra of quaternions that is defined by a product like given by this? How can I decode a rotation such as this one? And this is no trivial result. Actually, Hamilton, when he was walking, when he produced this, he was working on this for a very long time, and was only when he was walking through the canal with his wife that out of the sudden he came up with this idea that the product should be done by this, not exactly by this, but by something extremely similar that falls now into this. And he was so excited, and I read, actually, he was so excited that he felt the need to carve with a knife that result into a stone, which is today in Dublin, if you want to see it, which is quite fortunate because today is just one day after St. Patrick's Day that we're shooting this video. So we're going to celebrate today Quaternions and Hamilton in Dublin with that. In any case, a quaternion, for us to achieve that result, I will decode or perhaps reparameterize the quaternion as follows. The quaternion, any quaternion, can be written as a norm. So the norm of this quaternion is A plus a unitary direction of the quaternion in four-dimensional space. And that can be given by this. Now, I know that it feels like I just wrote this out of the blue, and indeed I have. So I know that the right result that we're looking for is this one, but we are going to go the other way around, right? It took several times for Hamilton to come up with those equations, so it's not trivial to go from what we want to do to those. Instead, we will go from the right answer and show you that indeed it works. So any quaternion can be parameterized as this, as a norm times a direction in four-dimensional space, and this direction in four-dimensional space can be further reparameterized into an unitary vector plus a sine of an angle and a cosine of angle over here. Okay, so take this. So just bear with me for a second with this formula, and I'm gonna show you that if we do the following operation, which is Q We will take the Q inverse, multiply that by a quaternion that we'll construct like this. We'll take 0 real part plus a imaginary part of U, and then multiply that by Q, and then I will show you that what we will have if we do this multiplication, assume the quaternion is decoded by that, we will in the end have this. We will have yet another quaternion which will have 0 part, and V will be the rotated vector according to this formula. So this is how we decode the quaternion rotations. This is how we can do rotations using only quaternions, and we will go through that. So I want to explore that a little bit, but just before, so let's think, just to make a parallel with complex numbers. Remember that a complex number was given by a phase, a gain plus a phase, right? And this, when you multiplied another complex number, this value would increase, would work as a gain. So this would increase the value of the gain. And this was as a phase. So you could use this as a gain for the vector itself. The complex number will increase by this factor over here. And also we'll have an additional phase, an additional angle that is given by this. And in a very similar way, I want you to think now that any quaternion can be written now as this, which will be a gain. So the norm of the quaternion is the gain, and this would be, in some sense, a 3D phase. Okay? So when you multiply quaternions, this multiplication, a multiplication of quaternions will add a phase and will add a gain. And the way to rotate quaternions is given by that. Now, we will go through this then, just to show you that that is indeed the case, and also to practice a little bit quaternion multiplication and other concepts that we'll see very shortly. So the inverse of a quaternion, again, the inverse of the quaternion is the inverse of the gain, times the conjugate, the quaternion conjugate, which, if you remember, we just need to invert the sign of the vector component. So this will go cosine of theta over 2 minus n sine of theta over 2, multiplied by 0 and u, multiplied by the quaternion itself, so multiplied by a times cosine of theta over 2 and sine of theta over 2. So if we work this a little bit, you can see that this a will cancel with this a over here. And now we need to choose a product to do. Quaternion product is associative, so we can choose to start either here or here. I will start maybe perhaps over here. So this will give us 1 over a cosine of theta over 2 minus n sine of theta over 2 quaternion product. And now we do this product over here. So notice that is the product of the real parts, which is 0 times something. You got 0 minus the dot product of those two. So it's minus a dot product, meaning that we're doing products of those two. So it's minus u. So this sign come over here, sine of theta 2, u dot product n. So this is what we get from the first part, and then we need to do this other part over here, which is the 0 times this vector plus cosine of theta over 2 times this vector over here. So we got the second one plus the cross product between those two. So the cross product of u and n sine of theta over 2. So this is the object. This is the final product of those two elements, and now we continue the product with the third one to see what we get. I'm very sorry, just this a was canceled, so this a is not here anymore. So what we have now, same formula, this element times that element over there, we have cosine, then the sine, and there is a minus over here. So there is a minus u dot product n, and then you have the dot product between those two. Now, it minus the dot product, so this minus will cancel with this minus, and you have a positive. And it's the dot product between this vector and those. Notice that this is parallel to n, and this one, this vector over here is perpendicular to n. And then you're going to do the dot product between a vector and a perpendicular vector, and therefore this second component does not count. It's going to be 0. And what you have is just sine of theta 2, cosine of theta 2, and n dot product u. Okay. And now we're going to do the second line. But notice for the first line that this term is equal to that term, so you already have 0 on the first line. And therefore, this result here is already valid. But what we want to compute then, it's what it's here. And we want to see if this value over here is indeed v. So let's do that. Let's compute this expression, which is p0, the first one. So this expression here will be cosine of theta 2 times this vector over here. So you have cosine squared times u plus u and cosine theta 2 sine theta 2, cosine theta 2 sine theta 2 plus that. Then you have now this value over here times this vector. So it's really minus with minus is a plus. You get sine of theta 2 and then n u dot n. And then the cross product of this vector and this vector over here. So the cross product, okay, so we'll add those up. We will have plus, I'll put it in 2 lines. So now we have a minus cross product of n sine of theta 2 and cross product u. And then you have also a cosine theta 2 minus sine theta 2 squared with an n cross product with this guy over here. Now this is the moment where we can exercise some vector algebra and some trigonometry. Let's see what we can do to, because in the end of the day we are hoping to get this, and we definitely don't have that yet. But let's see what we can do about that. First of all, we do have those terms that look, this term over here and this term over here, that looks very much alike, except that the dot product order is reversed. And the one we are looking for is u cross n. Therefore, I will change this one to u cross n instead. And I'm allowed to change this order if I change the sign, right? So I'm taking the second one. And if I do that, those terms are exactly the same, so I'm allowed to add them up. And if you do that, those two terms together, when you add them up, they will add them up to 2 sine of theta 2 cosine of theta 2 u cross n. And you can see from this, coming back from trigonometry, we have the double arc formulas. That tells us that if you have, for instance, sine of 2x, that's given by 2 sine of x cosine of x. And that's exactly what we have here, except that x is theta over 2, and therefore this sine is really 2 theta over 2, which is sine of theta. So in the end of the day, this part here is sine of theta, and then you have sine of theta u cross n as it should be. So we did find our first vector. Now we need to find those two. So the other term that I want to work a little bit is this one over here. This is what is called a triple product, and there is a formula that could help us a lot here, which is called the triple product expansion. So the triple product expansion is the formula in general is given by this. So if you have A cross B cross C, and the parentheses, they are right in this position, this can be written as a B, A dot product, with C, minus there's a minimum for that in English, which is called the back cab formula. So this is called the back of the cab formula. That helps you remember. That's how I remember. So we can use that. We can actually plug this over here. If you do that, if you use this expression in cross U cross N, what you have is the back, so B, U, the back, so A times the C, minus C, which is the last term, N. Sorry, this is N. A, B, so A and B, so N dot U. Okay, so we have that. Notice that N cross N is a unitary vector, so the dot product of vector of itself is really the norm, and the norm of this unitary vector is just 1, right? So this is really just U. And therefore, this term over here, we can rewrite it as sine squared of theta over 2 times U. So there's a minus here, we'll keep that minus over there. And minus this other term, although with that minus become a plus. Okay, so this minus with this minus is a plus of sine squared of theta 2 n dot U. So you have that. And now we have something very similar. You have this term and this term, which together gives you U cosine squared of theta dot over 2 minus z squared of theta over 2. And this term, on the other hand, it's yet another double arc formula. So this is for the double of sine, but you also have the cosine of 2x, which is given by cosine squared of x minus the sine squared of x. So this is the double formula for the cosine of x. And in this case, is exactly what we have over here. So we can really write this as U, this term here, as the cosine, as U cosine of theta. And we found this term. So we have the second term. And what remains should be this term over here. And indeed it is. So now the only two terms that remain are this term and this term. So I just missed a squared over here. And notice that this term there came from the product of those two. And therefore, there was a sign that I missed, but I'm putting it back. And then you will see that those two sine squared here will give you 2 sine squared, right? So here what you will have is 2 sine squared of theta over 2 n plus u. And you can play with this a little bit longer to find that if you use the fundamental trigonometry formula over here, that this cosine is really 1 minus sine squared. So then you have 1 minus sine squared with this sine squared becomes 2 sine squared. And therefore, you have that the 2 sine squared, 2 sine squared is really equal to 1 minus the cosine of 2x. And if that's theta over 2, then it becomes 1 minus cosine of theta, and you have this final term. So this is really the final term that we have over there, which is 1 minus cosine theta n over 1. And therefore, what you have is the rotation formula downstairs. So here, this is really V. That's what you have. And the main, this was a great exercise to come up with a lot of notions that you had before and how they build, so you can become really intimate with this process. But understand that the most important thing, the takeaway here, is that you are able to do this quaternion multiplication, and this process will give you the rotation of a vector itself. And since this was a left-hand rotation, either of the vector, you can see this as a left-hand rotation of the vector or a right-hand rotation of the reference frame. So if we rotate to the right, a fixed vector will rotate to the left. So this formula can also be seen as the right-hand rotation of a reference frame. So this is how the quaternion algebra comes together to help you to do rotations. And notice that while here we need trigonometric functions to perform this operation, here we do not. If I tell you what a quaternion is, and that quaternion will be 4 numbers, you can plug those 4 numbers here and do only polynomial operations, and you perform a rotation. So that's quite interesting, and we have yet even more interesting properties that we will explore perhaps later. But this was Hamilton was so excited that he had to carve on the stone, and that process up to this day is on a letter marked to his son.
But on the 16th day of the same month, which happened to be a Monday, and a council day of the Royal Irish Academy, I was walking in to attend and preside, and your mother was walking with me, along the Royal Canal, to which she had perhaps driven. And although she talked with me now and then, yet an undercurrent of thought was going on in my mind, which gave at last a result, whereof it is not too much to say that I felt at once the importance. An electric circuit seemed to close, and a spark flashed forth, the herald, as I foresaw, immediately, of many long years to come of definitely directed thought and work, by myself if spared, and at all events on the part of others, if I should even be allowed to live long enough distinctly to communicate the discovery. Nor could I resist the impulse, unphilosophical as it may have been, to cut with a knife on a stone of Brougham Bridge, as we passed it, the fundamental formula.
And the fundamental formula that he wrote were the bases that define quaternion multiplication that allows us to do what we just did.